Okay, I think we can start.
Yes, we can start. Okay, I can start?
Yes.
Okay. Good morning, everyone.
Good
It's a,
morning.
it's a pleasure to be here. I'm going to talk a little about of new paths to sustainable anodes in lithium-ion batteries. In this presentation, I will introduce general aspects of the topic, discuss graphite, the main anode for LIBs, and present sustainable approach such as recycled graphite from LIBs, and the production of carbon, silicon, and silicon carbide from biomass. And also comments briefly on life cycle assessment and conclusion. Batteries play an important role in the energy transition. The burn of fossil fuels release greenhouse gases, particulate matter, and air pollutants, leading to environmental problems and risk to human health. This is an immediate need to intensify the use of clean and renewable energy sources and as well as energy storage system to provide energy continuously and stably. LIBs dominate the market, powered everything from smartphones to electric vehicles. Graphite remains the most widely used anode material, but growing market demand is driving the development of alternative materials. Graphite is divided in two main groups, natural and synthetic graphite. Natural graphite occurs in rocks. The energy consumption is concentrated in the mining and rock process stage. It has an energy consumption of around 11,000 megajoules per ton. Synthetic graphite prepared through the carbonization and graphitization of organic precursor. The energy consumption is concentrated in the graphitization process, with temperatures above 2,500 Celsius degrees. The energy consumption is around 40,000 megajoules per ton. Figure 1 shows the global demand for LIBs from 2021 to 2030, and the projection indicated for 4735 gigawatts hours for 2030. Graphite accounts for 10 to 21% by weight in the composition of cylindrical, prismatic, and pouch cells, representing 8 to 10% of the LIBs costs. China dominates the graphite anode material industry, as can be seen in figure 2. The world's top graphite supplier for LIBs anodes are BTR for natural graphites and Shanshan for synthetic graphite. Now let's let's analyze the future demand for graphite. Of the 1.2 megatons of natural graphites per year, 15 to 20% are used in batteries for electric vehicles. Given the market growth, this number is projected to increase to 2.5 to 3 megatons of graphite per year. Another important information is that the graphite shortage is expected to begin in 2022, with the projected deficit of 80 megatons by 2040. So, the pros of using graphite are low cost, structural stability, well-established material in the industry, and the cons are limited capacity and future demand. The growing market demands for anode materials with higher energy density and power. In view of this, we have sustainable alternatives in focus as recycled graphite from LIBs, biomass-derived carbon, silicon, and silicon carbide. The pros of using recycled graphite from LIBs are sustainability and circular economy, and reduce raw material costs. The cons are complexity of recycling or separation, quality or purity of the recycled material as electrolyte resid, lithium salts, or binder, and underdeveloped technologies. The table 1 shows the recycle methods and electrochemical performance of the recycled graphite material for used in LIBs. The main methods used on it is flotation, rapid thermal shock, and acid leaching. The pros of using biomass-derived carbons are porous structures, high abundance, low cost, and good electrochemical performance. And the cons are low diffusion kinetics and relative intermittent storage sites. Table 2 shows the feedstock, the method, the production method, and the performance of biomass-derived carbon applied to LIBs. Some of these materials are pomelo peels, corn stalk, peanut shells, rice husk, sugarcane bagasse, and wet straw. The main synthesis methods for biomass-derived carbons are divided in two groups: carbonization and activation. The carbonization methods are pyrolysis, hydrothermal carbonization, and hydrothermal liquefaction. And activation methods are physical, chemical, microwave, and molten salt. The pyrolysis is a thermochemical process that decomposes organic materials at high temperatures in absence of oxygen, resulting in the production of biochar, bio-oil, and syngas. The advantages of these methods are simple to operate, applicable to a wide range of pressure, easy recovery of the samples, high crystallinity of carbon materials, and mature process. And the disadvantages are multiple steps process and carbon material is not activated. The hydrothermal carbonization is a process performed at low temperature and self-generated pressures, with external heating to produce solid carbon material from biomass. Water is generally used as the reaction medium. The advantages are low-cost process, low energy consumptions, high carbon yields, mature process, and processed wet raw material. The disadvantages are high equipment requirement, carbon material not activate, and not suitable for large-scale production. The hydrothermal liquefaction is a process that uses low temperatures and high pressures to convert the biomass into oil, gas, aqueous phase, and solid residue. And water is also generally used as the reaction medium. The advantages are processing wet raw material, compatibility with various raw materials, and produce multiple products. The disadvantages are limited commercial material and high capital costs. The physical activation is a process operated at high temperature using oxidizing gases as water vapor, CO2, and air for the preparation of carbon materials. The advantages are simple operation process, low corrosion to equipment, and the disadvantages are high activation temperature and long activation time. Structures of carbon material are often disordered, and the pore shapes and size cannot be accurately controlled. The chemical activation uses chemical activators, and the carbonization and activation are conducted at high temperatures in an inert atmosphere. The advantages are simple and convenient to operate, applicable to a wide range of precursors, easy recovery of the samples, high crystallinity of the carbon materials and material process. The disadvantages are multiple step process and carbon material is not activated. The microwave assisted activation use heat treatment in which microwave are used to rapidly heat the precursor material. The advantages are simple operation and short residence time, fast heating rate, small equipment size, produce carbon material with high specific surface area, and suitable for large-scale production. The disadvantages are the reaction temperature of the material cannot be precisely controlled, and the excessive microwave radiation is harmful to health. And the molten salt activation using metal salts in the reaction in the reaction system under inert temperature and inert atmosphere, and with temperature ranging from 450 to 850 Celsius degree. The advantages are simple synthesis process, single thermal process, short residence time, heteroatoms can be doped in carbons from the salts, high crystallinity of carbon materials with a large specific surface area, and the disadvantages are high energy consumption, strong salt product interactions, corrosion of the equipment, low carbon yields, and possible generation of byproducts. The pros of using biomass-derived silicones are high capacity, high energy density, high abundance available material. And the cons are significant volumetric expansion, low intrinsic electroconductive, and unstable solid electrolyte interface. Table 3 shows the feedstock, the production method, and the electrochemical performance of the biomass-derived silicon applied to LIBs. Some of these feedstocks are waste coffee grounds, sugarcane leaves, barley straw, rice husk, and bamboo leaves. The production methods are carbothermal reduction, that is similar to a high temperature pyrolysis, and low temperature pyrolysis followed by acid deletion and reaction with magnesium, zinc, or aluminum in an inert atmosphere. The pros of using biomass-derived silicon carbide are mechanical robustness, thermal and chemical stability, and high specific capacity. And the cons are low electrical conductivity, concerns about process scalability, and energy efficiency. Table 4 show the barley and rice husk used as feedstock and good electrochemical performance of silicon carbide in LIBs. Other materials used in the silicon carbide production were found in literature such as glass and post-consumer coffee grounds, rubber, bamboo, macadamia shell, macroalga, and corn stalk. Speaking a little about life cycle assessment, studies suggest that the biomass-derived carbon material are more eco-friendly than the commercial carbon material. For example, Sivaram and collaborator used Posopolis juliflora biochar for supercapacitor and found lower global warming potential than commercial activated carbon. And Derestiller and collaborators convert upcycling waste coffee into spherical graphene for supercapacitor and found reduction of CO2 emissions and environmental impact compared to graphene produced with conventional manufacture techniques. In conclusion, graphite still dominates the market but faces capacity and supply limitation. Sustainable alternative as recycled graphite, biomass-derived carbon, silicon, and silicon carbide offer higher performance and low environmental impacts through technical challenge remains. This approach represents promising pathways to overcome the current limitation of graphite in LIBs. So thank you.
Thank you, Anna. Great presentation.
Thank you.
Does anybody have a question? Is this graphite carbon production the activated carbon that of project 2 in AES?
We have some people that works with some activate carbons, and I am working with the production of silicon carbide biomass material from the node too. And we have some good results and other will be not so good one. This is a huge task, you know. We have a lot. I perform a lot of tests and I'm testing different things in the synthesis and with the ink too. And I expect to be good things, good results with it.
Good.
Yeah.
Any other question? Yeah, Rafael.
Hi, Anna. Can you hear me?
Yes.
Okay, thank you for the talk. My question is about, so you use this biomass to design your batteries, right?
Mm-hmm.
So, but after the lifetime of your battery, what happened with this biomass again? The materials you use to build up your battery.
Yes, the material that we'll use with this in this battery will be waste as other ones that are used with with graphite or other active material that you use. But the good thing with it is use a feedstock that produce less environmental problem than the one that is in the beginning. This is it. The
Okay.
idea is it.
Okay, thank you.
Anyone else? I heard you just published a paper.
Yeah, it's one about silicon carbide. A review in about the literature that we saw green point of view of use silicon carbide as anode in LIBs. And we talk about many of these feedstocks, but the most part of it is not effectively used for LIBs. There is a lot of things related to the production of silicon carbide, but not applied to LIBs. And there is one another that is applied. Of course, there is a lot of applied with the feedstocks that are not provenient of recycled material or biomass. And we take all this information with other information about in production too, and we put it on this review. That is a good news that we have today.
Congratulations.
Yes, the paper is already accepted and will be published on future.
Yeah. Okay. Congratulations.
Thank you.
Anybody else? Okay, let's thank again Anna. Great
Thank you.
presentation. And we see you in 2 weeks for another CINE Talks. Thank you, guys. Have a
Thank
great
you.
weekend.